Hi, and welcome to the Build Your Own Data Logger course, brought to you by FreakLabs and WildLabs. I'm Akiba from FreakLabs. This is Module 6-1, Ruggedizing the Forgotten Heroes of Field Devices, the Cables, Connectors, and User Interfaces. Cables and connectors can make or break a field setup, so let's go through some ways we can protect them. And just a note, for the components that we'll be discussing here, we'll also be providing links to them in our web shop. We work hard on locating suppliers for ruggedization components, so if you see anything you think is interesting, feel free to pick some up and try them out. In this video, we'll cover how to select the correct wires by understanding the wire gauge, type, and binding. We'll also look at different ways you can connect peripherals to your device using cable harnesses, cable glands, and various connectors inside and the outside of the enclosure. We'll also cover some techniques for waterproofing LEDs and push buttons if they're exposed to the elements. Let's start from the beginning. What is a cable, really? A cable is a collection of wires, usually of the same gauge, bound together in a particular way and enclosed in some kind of protective sheath. There are many types of cables made from materials and coverings depending on the application and environment they're used in. For example, there's power cables, audio cables, USB cables, underwater fiber optic cables. Well, you get the picture. The cables we're interested in are electrical cables, made from copper wires and either enclosed in a PVC sheath or bundled together in a cable harness. We'll also briefly go over the different types of cables, such as shielded cables, twisted pairs, and coaxial cables, which, along with standard straight cables, are commonly encountered in field devices. When selecting or making cables, there are two things to consider: the wire gauge and the binding. A wire's gauge is how thick a wire is, and this determines how much current can flow through the wire. This is important because if the current flowing through the wire is higher than its current carrying capacity, the wire can overheat, melt things, and cause fires. Although wire gauges can be measured in metric, a lot of the industry uses the American Wire Gauge, or AWG, system. The smaller the AWG, the thicker the wire, and the more current capacity the wire has. For example, a wire with an AWG rating of 20 has a current capacity of around 1.4 amps, while a wire with an AWG rating of 30 has a current capacity of approximately 140 milliamps or 0.14 amps. Other factors can also affect the current capacity, such as the material the wires are made from, but for now, we'll just focus on copper wires, which are the most common type. Here's a chart of the AWG ratings and the current capacity. If we want to interface a sensor to a system and it doesn't use a lot of current, we could specify something like a 28 AWG cable. This would mean that the individual wires could carry up to 250 milliamps of current. For power cables, like battery or solar panels, you need to be much more conscientious of the amount of current that will be used in the system. Interestingly, in some cases, the limiting factor to how big the battery or solar panels are comes from the cable's wire gauge, which determines the current carrying capacity. For the WildLogger, we're using 26 AWG for the batteries, which has a current capacity of 400 milliamps. On the sensors, we're using 28 AWG, which has a current capacity of 250 milliamps. In general, for signal cables, 28 AWG is normally fine since they won't carry a lot of current. For battery or power cables, you'll need to understand the current carrying requirements to figure out the wire gauge. Now let's look at how the wires are bound together. In the WildLogger, we're using discrete insulated wires with a PVC insulation. By discrete, I mean there's no bundling sheath. It's just bare wires and insulation. You can see these wires in the top picture. Another common cable that is used are sheath cables, as in the pictures below. These are cables that consist of two or more insulated wires or cores, which are then bound or braided together and enclosed in a sheath. A sheath is essentially an insulating tube that bundles the cores together. The sheath is usually made from PVC, silicone, or some other insulating material. Two of the most common types of shielded cables are RVV, which is a standard sheathed multi-core cable, and RVVP, which is the shielded version of RVV. We'll explain more about shielded cables in the next slide. Multi-core sheath cable is commonly used in conjunction with external cable connectors to connect instrumentation devices together. Discrete insulated wires are usually used internally in a device. As we just mentioned, sheath cables can also come in a shielded form. The shield is in the form of a conductive jacket around the wire bundle, which is grounded to the devices they're connected to. We won't get into too much detail on shielding, but it prevents noise from getting picked up in the cables, which could be very important for sensitive signals, such as analog audio signals from a high-end microphone. Twisted pair cables use another technique to suppress noise on sensitive signals. By twisting the wires and running the signals in a specific way, i.e. differentially, you can get the noise to cancel each other out. This also prevents the wire from radiating electromagnetic waves outward, which can cause interference to other devices. This type of configuration is often used to carry fast signals and is the standard cable type for high-speed Ethernet and a lot of factory networking systems. If you've ever opened up the insulation from a Category 5 Ethernet cable, you'll see the twisted pairs exposed. In a wildlife field scenario, we generally only use this type of cable for communications, like if we needed to connect a field device to an Ethernet device or a computer. Finally, if you're using wireless and connecting to big antennas, you'll likely be using coaxial or antenna cables. Coaxial cables typically consist of a single inner wire running coaxially or in parallel to an outer conductor, which acts as a shield. The shield is precisely spaced from the inner wire to maintain a specific resistance, usually 50 ohms. We'll primarily use coaxial cables for wireless connections from a field device to an external antenna. One of the unsung heroes of device design are cable harnesses. A cable harness allows you to easily connect and disconnect a group of cables. On the WildLogger, we've used cable harnesses to connect peripherals like the DHT11, PIR motion sensor, programming dongle, and the battery pack to the board. There are multiple benefits for using cable harnesses. They make devices easier and quicker to assemble and disassemble. They can only be inserted one way, aka, like US politics, they're polarized. They ensure that the ground wire is going to the ground pin and the power wire is going to the power pin. This is crucial because if wires are connected backwards, it can damage the whole device. Finally, cable harnesses prevent the cables from being yanked out or falling out due to vibration. These are all very common causes of device failure. As you deal more with custom devices, I'm sure you'll come to appreciate the convenience of cable harnesses and how much they can increase the robustness of the system. Cable harnesses are comprised of a plug and a receptacle, where the plug is inserted into the receptacle to make electrical contact. A plug or receptacle consists of three parts: the wire, the terminal, which is the electrical contact, and the housing. We'll show how these get assembled together in a bit. There's a huge array of cable harness connectors available. We'll look at two specific types: board-to-cable and cable-to-cable. Board-to-cable connectors are used for things like connecting sensors, speakers, or battery packs directly to the board. For these, we use the XH family of connectors from the manufacturer JST. These have a spacing, or pitch, of 2.54 millimeters, or 0.1 inches. Pitch is the spacing between electrical contacts. So a 2.54 millimeter pitch means that it's 2.54 millimeters between electrical contacts. Some popular connectors, like the JST PH series, have a pitch of 2 millimeters, which means there's a 2 millimeter spacing between the contacts. There are also the majority of the connectors that you'll find on the WildLogger board. Cable connectors are used to connect one cable to another, rather than connecting directly to a board. They're useful to connect peripherals without having to open up the enclosure and access the board directly, or to extend the length of a cable for a speaker, for example. For cable-to-cable connectors, we use the JST SM family of connectors, which also have a 2.54 millimeter or 0.1 inch pitch. The cables on WildLogger already have cable harnesses. In the next video, 6-2, we'll show you how to thread them through the cable gland. So what's a cable gland? A cable gland allows us to create a watertight hole in the enclosure through which we can thread cables. Cable glands are rated at IP68, which means they're submersible. However, it's important to match the size of the cable gland to the size of the cables as much as possible and have them correctly fitted. Also, if you plan on having the cable gland submerged in water, we recommend testing it first with the cable that will be used to guarantee that no water will leak through the system. First, let's look at what makes up a cable gland. Starting from left to right, A, B, and C fasten the cable gland to the enclosure. From outside the enclosure, the washer and cable gland body is inserted into the opening. The lock nut is then screwed onto the back of the cable gland and fastens it to the enclosure. The right-hand side components, C, D, E, and F, are for the compression seal on the cable and sit on the outside of the enclosure. Usually, these parts are pre-assembled, so you wouldn't need to manually put them together. The seal is inside the claw, and the sealing nut goes over the claw. As the sealing nut is tightened, it compresses the claw, tightening the seal around the cable. Once the seal is tightened down around the cable gland should keep the enclosure watertight. The advantage of cable glands is that they're a relatively cheap and easy way to create a watertight seal around the hole the cables go through. The drawback is they're quite permanent. Once the cable is fed through the gland and the connector housings are inserted, you can't really remove the cables without cutting off the wire harness connectors or disassembling them. So for example, in the case of a field repair for WildLogger, if the sensor cable goes bad, you can't just replace the cable. You'd have to either swap out the complete cable assembly, including the cable gland, or recrimp a new cable in the field. So now let's look at some other connectivity options that get around this. For setups that need to be broken down easily, you may want to consider using external connectors, which can attach and detach peripherals without opening the enclosure or destroying the cable gland. External connectors cost more than cable glands, and there are many types. We'll be covering some basic, common external connector families, including barrel jack connectors, aviation connectors, SP connectors, and M connectors. External connectors can get quite fancy and very pricey, but these ones provide a good balance between performance and price. Panel mount barrel jack connectors are low-cost connectors commonly used for power inputs. You can often find them on the back of your network router or electrical devices. You can get barrel jack connectors off the shelf, and they fit the 2.1mm plug, which is the main size found on AC/DC adapters, aka wall warts. They're only built for 2 wires, power and ground, and can typically handle up to 5 amps of current. Hence, they're a good choice if you're planning to run an external DC power source like a 12-volt battery into your design, or interface some solar panels. The ones we typically use and sell come with a plug cover as well to prevent moisture from entering the plug when not in use. These connectors aren't waterproof, however, so if you'll be using them in an exposed setting, you'll need to use secondary protection to prevent moisture. This could be electrical tape, silicone sealant, rubber cement, etc. Here's a shot of how a panel mount barrel jack connector looks when it's mounted on an enclosure. It allows for easy access to plug in an AC/DC adapter, say to charge a battery. It's also handy for plugging in a solar panel to charge the system. You'd have to add additional sealant to the interface between the connector and the plug, since it's not a waterproof interface though. Aviation connectors refer to a family of threaded external connectors. They provide good protection against getting yanked out since the locking cap needs to be screwed on. These are also relatively low-cost external connectors. These connectors are also, unfortunately, not waterproof and would also require secondary protection to seal the gaps and make them waterproof. We often use these connectors in conjunction with electrical tape or heat shrink tubing as a way to have a low-cost, robust, and waterproof interconnect between our instrumentation devices and sensor boxes. Here are some shots of how the aviation connectors look mounted on an enclosure. The top picture shows how they're capped when not being used. The bottom picture shows a sheathed cable with the aviation plug connector screwed into the receptacle. And the right-hand picture shows the discrete wire harnesses coming out of the receptacles inside the enclosure. The SP connectors are heavier duty connectors than the Aviation GX connectors and are IP68 rated, so are waterproof. The different sizes relate to the diameter of the hole that needs to be drilled out. The larger the diameter, the more pins the connector can fit. The receptacles are covered, and there's a threaded locking cap with waterproof gaskets so that the connection is protected from water. On the other side, there's a compression seal for cabling so that water can't sneak in that way either. These connectors provide a good balance between cost and robustness, especially if you'll be deploying in harsh environments. Here are some shots of an SP13 mounted on an enclosure. The top left image shows the receptacle with the cap on. The bottom image and top right image show the connector with the plug mated to it. M connectors were originally designed for harsh factory environments. They have an all-metal receptacle and plug and are designed for cables that are often dropped. They also come in different sizes which relate to the mounting hole and therefore how thick the wire cable can be. These connectors are quite expensive and industrial grade, but are designed to last very long or withstand very harsh environments. They're precision machined to protect against high shock and vibration scenarios and are waterproof and dustproof. Finally, let's look at some interesting ways to protect user interfaces. If your device has a button interface that's exposed, you'll want to waterproof that as well. Luckily, waterproof buttons exist. These buttons are specifically designed to allow for event signaling from a button, but prevent moisture from entering the button housing and hole. These typically have a mounting gasket, and the internal design provides a seal so water won't enter via the button switch mechanism. If your device has external facing LEDs that need to be waterproofed, you can use what's called LED sockets. Basically, the LED sits within the socket, and the socket size needs to match the LED size, which is usually 3mm or 5mm. LED sockets also contain a gasket for the mounting screw, and need to be internally sealed after the LED is mounted. You can use rubber cement or any liquid sealant to do this. In this lab, we learned about some of our options for ruggedizing our cables, connectors, and user interfaces, as well as putting together wire harnesses to connect cables to cables and cables to boards. For field devices, the mechanical design choices are just as important as the technology design, since they all contribute to what we're really after, maximizing our field life. Coming up in the next video, we'll be putting together our WildLogger based on what we've just learned. Join us for Module 6-2, Assembling the WildLogger.